You've definitely used this chemical, probably without even realizing it.
And yep, it's even the thing that helps get the caffeine out of your coffee beans. We're talking about a chemical called ethyl acetate. So this stuff is everywhere, but making it, well, that's the tricky part. How do you do it efficiently and, more importantly, in a way that's actually good for the environment? That's a huge puzzle for chemical engineers. So today, we're going to dive into the quest for what's called green ethyl acetate. We'll look at how a couple of scientists, Piotkovsky and Kalutsny, tackled this exact problem head-on in their research. All right, so here's our game plan. First, we'll cover the basics. What is ethyl acetate? Then we'll get into that production puzzle I mentioned. From there, we'll check out a much greener experiment, its big aha moment, and of course, the final results. And we'll wrap up with the big one, why any of this really matters. All right, first things first, what exactly is this stuff we keep talking about? Well, ethyl acetate is often called a green chemical. And for good reason. It's a really popular solvent, mostly because it has low toxicity and it's biodegradable. That's a massive win for the environment, right? Now, if you look at the chemistry on paper, making it seems super simple. It's a classic reaction. You might have even heard of it, called Fischer esterification. You just take some ethanol, that's an alcohol, and mix it with acetic acid, which, is basically what makes vinegar sour. Boom, you get ethyl acetate and a little bit of water. Sounds easy, right? Well, not so fast. Because that simple-looking reaction, it creates a really, really stubborn problem. I like to think of it as the inseparable trio. So this problem has a name. It's called an azeotrope. It's a pretty wild chemical phenomenon. The best way to think about it is like a perfect cocktail where all the ingredients are so tightly bonded that they literally boil at the exact same temperature. And that's a huge deal, because it means you can't just boil them off one by one to separate them. Normal distillation, totally useless here. And here's what that stubborn mix actually looks like. You've got the ethyl acetate you want, sure, but it's chemically handcuffed to the leftover ethanol and water. The three of them form this ternary azeotrope, and figuring out how to break them up, well, that is the heart of the whole production puzzle. So how in the world do you solve a puzzle like that? This is where we get to the really cool part, the experiment that's at the center of this research. It was all about finding a greener, smarter, and way more efficient way to break up that inseparable trio. And listen, their goals were incredibly ambitious. They weren't just trying to find a solution. They wanted to make the whole process better in just about every way you can measure. We're talking less fresh water, less wastewater, recovering more of the raw materials, cranking the product purity up past 99.9%. Oh, and doing it all while using less energy. Talk about a high bar. And their core theory, it was actually beautiful in its simplicity. It all boils down to this concept called phase equilibrium. Just think of it like the physical balance between all the liquids in the mix. Their big idea, their hypothesis, was that if they just changed one key thing, the temperature, right before they washed the mixture with water, they could totally shift that balance. Basically make the liquids less sticky, making them way easier to pull apart. Okay. And this is where it gets really, really good. Let's dig into the key observation, that aha moment where this simple little theory proved to be a seriously powerful solution. So what was the big secret? What was the one simple tweak that made all the difference? The key to finally breaking up that stubborn azeotrope. You ready for this? It was all about temperature. See, the classic way of doing things involves washing the mixture when it's warm, around 70 degrees Celsius. The big breakthrough was to do the complete opposite. They subcooled the mixture, dropping it all the way down to 30 degrees Celsius before washing it with water. So that 40-degree temperature drop, that was everything. That was the secret sauce. See, by making a whole mixture colder, the ethyl acetate suddenly doesn't want to dissolve in the wash water anymore. But the ethanol? Oh, it happily jumps into the water. And just like that, this one simple change forces a much, much cleaner separation. It leaves you with a solution that's packed with the pure ethyl acetate they wanted all along. So the theory was great, and it actually worked in the real world. But the big question is, just how much better was this new method? Well, the final results leave no doubt. There was a clear, undeniable winner. Okay, take a look at this table from the study. It lays it all out, comparing the old process with the new one. And get this. The product purity skyrockets from 98% to an incredible 99.9%. At the very same time, you can see the amount of fresh water and wastewater you need for every ton of product. It just drops, big time. And we're not talking small changes here. These numbers are huge. We're looking at almost a 32% drop in wastewater and a nearly 35% drop in freshwater use. Now, imagine that at the scale of a huge industrial plant. That is a massive, massive win, both for the company's bank account and for the planet.
But honestly, here's the number that just blew my mind. The amount of organic gunk, the pollution in the wastewater, it was reduced by a factor of 9. 9 times less. That's not just an improvement, that's a total game changer. It's a fundamental leap forward in making this whole process cleaner.
So let's step back for a second. A simple temperature change leads to these incredible gains. But why does this matter beyond just, making nail polish remover? Let's zoom out and look at the bigger picture of what we call green chemistry. This quote from the researchers who did the work, it just says it all, doesn't it? This isn't just about one little technical fix for one chemical process. It's about a whole philosophy, a mindset of sustainable engineering. It's all about pushing us towards what they call a closed cycle economy, one where we're constantly trying to minimize waste and maximize every bit of energy and material we use. And to think, this whole breakthrough, all these benefits, they all came from just rethinking one single, simple variable. It really makes you wonder, doesn't it? How many other invisible industrial processes, the ones making all the stuff we use every single day, are just sitting there waiting to be completely transformed by one simple, clever idea?